Hi everybody, in this video we are going to be talking about electron configuration. But first, let's talk about electrons. We know that atoms have electrons. These electrons are scattered all over the place and have certain energy levels. Now, an electron configuration arranges all the electrons in such a way that lists them from their lowest energy level to the highest energy level. And they can be listed in other ways, but in this video I am going to order my electrons in terms of energy level for the purposes of consistency. So, let's look at the staircase. Using the staircase, you can order the orbitals in terms of their energy level. So, let me teach you how that is done. Let's start off by doing a diagonal line and doing a second diagonal line, a third one, a fourth one, a fifth one, a sixth one, a seventh one, and an eighth one. So notice how these diagonal lines are, they're like 45 degrees from the horizontal. So be sure to draw your diagonal lines correctly when doing the staircase trick. So I will show you how to read the staircase, and this will tell you the order that the orbitals come in terms of their energy. So, by reading this, we read it by diagonal, and we go down the list, and we go from the top of the diagonal to the bottom of the diagonal. So let me just show you. So we start off with the first diagonal, which contains the 1s. The second diagonal contains 2s. The third diagonal contains 2p and 3s. The fourth diagonal contains 3p and 4s. The fifth diagonal contains 3d, 4p, 5s. The sixth diagonal contains 4d, 5p, and 6s. And the seventh diagonal has 4f, 5d, 6p, 7s, and reading the last diagonal we get 5f, 6d, 7p, and 8s. And this is the order in which the orbitals are in terms of lowest energy to highest energy. So there's one thing to note. Notice how in this list the 3d electrons have higher energy than the 4s electrons, and the reason for this is something that is probably beyond this course, so I won't talk about it. But in general, what I can say is that these numbers tell you which one is farther away. So for example, the 4s electrons will be located farther away from the nucleus than the 3d electrons. However, the 4s electrons will have a lower energy state than the 3d electrons, which might have a higher energy state. So in general, the principal energy level, denoted as N, tells you how far something is, and it gives you an idea of how much energy something has, because the farther away an electron is, the more energy it has. But it's not always true, and sometimes exceptions come, such as here, where the 3d electrons have more energy than the 4s electrons. So in general, the number that's in front of the sublevel will tell you how far the electron is from the nucleus, but in order to know how much energy it has when compared to another thing, it's best if you use the staircase trick. So energy would be equal to staircase. So just keep a note on that, and you'll see it pop up later when we talk about something called valence electrons. So let's move on and talk about electron configuration. So electron configuration tells us the electrons in an atom or ion in an increasing order of energy, typically. So if you remember, each orbital holds at most 2 electrons. For example, The s sublevel has 1 orbital, so it can hold at most 2 electrons. The p sublevel has 3 types of orbitals, which altogether can hold at most 6 electrons. The d sublevel has 5 types of orbitals, and they together can hold up to 10 electrons. And the f sublevel can hold at most 14 electrons because there are 7 types of f orbitals that exist. So note that these are just the maximum number of electrons they can have. They can actually hold less than that. Now let's go back to this image and let's write how many electrons are in each of these sublevels. So for the 1s sublevel, there's only one 1s orbital, so we will put a 2 here because there are 2 electrons in 1 orbital. Now same goes for the 2s sublevel. The 2s sublevel has only one 2s orbital, so it can hold at most 2 electrons. So what about the 2p orbital? Well, there are 3 types of 2p orbitals in the p sublevel, so they can hold at most 6 electrons, so I'll write a 6. And the s sublevel can hold 2, the p sublevel can hold 6, the s sublevel can hold 2, the d sublevel can hold 10, because, you know, there are 5 types of d orbitals in the d sublevel if you watched the previous video and saw the final image in the video. Now the 4p sublevel has 3 types of orbitals, 4px, 4py, 4pz, and this applies to the 2p sublevel too because you have 2px, 2py, 2pz. So there are 6 electrons that you can hold at most since there are only 3 types of orbitals, and each orbital can hold 2. So I'm being pretty redundant right now, so let me just fill in the blanks. So the 5s can hold 2 electrons at most. The 4d sublevel can hold 10 electrons at most. 5p is 6, s is 2, f is 14 because there are 7 types of f orbitals in the f sublevel. D is 10, p is 6, s is 2, f is 14, d is 10, p is 6 and 8, s is 2. So now that we've labeled the number of electrons in each sublevel, now let's go back to here and actually talk about how this actually applies. So let's do the electron configuration for sodium. So sodium has an atomic number of 11, so it has 11 protons, and in an atom, the number of protons and electrons are the same in order to add up to be neutral. So there are 11 electrons. So we have to use this energy chart in order to order our electrons from lowest energy to the highest energy, and we can only have 11 electrons. So we start off by filling out the 1s sublevel, and this can hold at most 2, and then the 2s sublevel, which can hold at most 2, and then the 2p sublevel, which can hold at most 6. And notice how we're going by the order of which the staircase goes. And then we have 10 electrons, since 2 electrons here, 2 electrons here, and 6 electrons there. And then last but not least, we have the 3s sublevel, and this can hold at most 2. But since we have only 1 electron left, because this is already 10, then we have to put a 1 there. And that is the electron configuration for sodium. So notice how this goes from the lowest to the highest energy level, and we only filled the electrons up to the amount that we had, which was 11. So now that I showed you this example, let's look at some principles or theories that are behind this. So Aufbau's principle states that electrons like to fill lower energy levels before moving on to the next. So, for example, the electrons in sodium like to fill in lower energy states before moving on to the next. Now let's look at our second rule. Hund's rule states that electrons only pair up after one electron has occupied every orbital in the sublevel. So I'll show you what that means by talking about something called orbital diagrams. Orbital diagrams are visual representations of the electron configuration. So in the previous video, if you remember, I could write the 1s orbital and its 2 electrons like this with up and down hooks. And then the 2s orbital can hold almost 2 electrons, so up and down hook. The 2p orbitals can hold at most 6 electrons, so there are 3 spaces, each representing one type of p orbital. And then I draw the up hooks first, and then I pair them up. And then last but not least, I write the 3s orbital, and I only have 1 electron there. So Hund's rule states that electrons only pair up after 1 electron has occupied every orbital in the sublevel. So for example, in the 2p sublevel, I had to make sure that each orbital had at least 1 electron before I started pairing them up. And you saw me do that because I did the up arrows first and then I went to the down arrows. So that's what Hund's rule is. And when an atom has electrons that are in their lowest energy states, or in other words, when the electrons are stacked from the lowest energy possible to the highest energy possible, then this is called the ground state configuration for the atom, since the electrons are stacked from the lowest they can go to the highest that they can go in the order at which the orbitals come in terms of energy. So that's what ground state is. And let's now move on to another topic. The abbreviated electron configuration is basically the electron configuration that we just went over a minute ago, but electrons that are part of the latest noble gas are substituted for the name of the noble gas. So let me just show you an example of how that works. So notice how sodium is 11, and let me do that in a different color. Sodium is 11, and the latest noble gas will be the noble gas in the previous period, which will be neon. And so you write neon, and notice how neon has 10 electrons, and notice how 1s2, 2s2, 2p6 contains 10 electrons. So the electrons here are the same as the electrons in neon, so that's why I could substitute it. And then the 3s1, of course, is separate, and you just add that on. So notice how the abbreviated electron configuration shortens the electron configuration significantly by using the electrons found in the noble gas as like a placeholder. So that's something cool that you could do. And now let's move on to the next topic. We have what are called S, P, D, and F blocks. And these are located on the periodic table as shown here, and they are color-coded. And these blocks work basically by taking the last electron of the elements that lie in these types of orbitals. And I don't think that makes sense when it comes out in words, but let's just look at an example and it will make sense from there. Transition metals have their last electrons in the d orbital, so these are the transition metals. And therefore, transition metals are in the d block since their last electrons or their final electrons are in the d orbital. So what block would sodium belong in? Well, sodium belongs in the s block because we found that the last electron is in the s orbital, so it will be in the s block. So that's how the blocks work, and let me teach you a nice trick to find the electron configurations based on just where it is located on the periodic table. So let's just say I wanted to find the electron configuration for sodium. So here's what I do. I look at sodium right there. I take a look at the previous period, and I take the neon gas, which is the quote-unquote final noble gas that comes before sodium, and this can be written as neon. And let me write that a little bit more clearly. So you're going to have a bracket and you're going to write neon, and then you're going to read the chart or simply just memorize it. So I'd say that memorizing it is quite easy because the row number is equal to the number that comes in front of the sublevel. So the first row will always have a 1, and this only applies for the S and P block. Now for the D block, it starts with 3D and then goes 4D, 5D, and 6D. For the F blocks, well, it starts with 4F and then 5F. So simply memorize those and you'll see how much easier it is to do electron configurations. So after we write neon, we simply have to look at here and we say, oh, this is where the 3s electrons are. So here, I just say, oh, well, sodium is just one more electron than neon, so 3s1. And why 3s? Well, because over here it says 3s. So simply memorizing this chart can really save you a lot of time. Let's do another example. Let's take a look at the electron configuration for something like, I don't know, let's see, astatine. Wow, astatine is pretty far down in the list, but we could handle this accordingly by taking the previous noble gas, which is xenon. So I'm going to write xenon, and I'm going to go from xenon and then go up in terms of energy level. So this can be a little bit dangerous. So let's look at where xenon lies in terms of energy. So its final electron is in the 5p orbital. So take a look at the staircase. The 5p orbital is there. And then it says afterwards you go to 6s for F, 5d, and 6p and 7f. So we have to follow this order. So be careful and do not skip any of these. So we end with 5p6 because the noble gas's last electron is in the 5p orbital. And now let's move accordingly. So typically, periodic tables don't look like that. They look like this. So use this to help you. Xenon has 54 electrons. Now astatine has 85. So by writing xenon, we accounted for 54 electrons, but there seems to be a lot more before we get to 85. So it seems like we have to be a bit careful with our math. So let's see how many more electrons we need to add to get to 85. So let's start off by doing the 6s2, which comes after 5p. So this would be 6s2. And after 6s2, we have 4f14. So let's write that, 4f14. And then after that, we have 5d10. And then let's see if we have exceeded the amount of electrons. So 54 to 85. So far, we have accounted for 16 plus 10. This accounts for 26 electrons so far. So 54 plus 26 is equal to 80. And it looks like we're 5 away from 85. So we just need to add 5 more electrons. So what comes after 5d10? Well, afterwards it comes 6p. So we have to write 6p, and we have to be careful because we only need 5 electrons to get from 80 to 85. So we don't need all 6 of the 6p electrons, we only need 5 of them. And that's how you write the electron configuration for something more complicated like astatine. Now, if you really want to know how to read this and become an expert, simply follow my lead and look at where my arrow goes. So remember, every time you're adding a proton, in other words, you're going from one element to the other, you are adding an electron, and it goes from lower energy level to higher energy level. So keep a mental image of this chart here and how it relates to this chart, and let's go up the periodic table. So 1s2, because there are only 2 elements that can fit in here because there are 2 electrons, and then 2s2, 2p6, 3s2, 3p6, 4s2, and let me make sure that only covers 2 elements, and then 3d10, and then 4p6, 5s2, 4d10, 5p6, Now I'm going a little bit slower because it's getting a lot more complicated. And then it goes 6s2, and then here's where things get a little bit wacky. So lanthanum's actually in the 5d sublevel, but after 6s, we're supposed to go to, well, the 4f sublevel. So we have to go to the 4f sublevel first, which is down here. So skip lanthanum, and this is 4f14, and then it goes back to 5d10, and then 6p6, and then it goes to 7s2, and then it goes to 5f14, and then it goes to 6d10, and last but not least, it goes to, what row is this? This is 7p6, and that's the order at which the orbitals go for these elements. And remember how lanthanum and actinium jumped from the 5d and 6d sublevels respectively to the f sublevels, and then it went straight back to the d sublevels. So these are some exceptions to electron configurations on the periodic table, and it goes to show that not everything is predictable in chemistry. So, for example, lanthanum's last electron is in the 5d sublevel, and then cerium's last electron suddenly becomes in the 4f sublevel. And then for praseodymium, what happens is that the 5d electron hops into the 4f sublevel, and suddenly you have 4f3. So it is complicated, but this is just to show one exception that happens. And notice how these electron configurations here break one of the rules we learned. It actually breaks Aufbau's principle, since it states that electrons like to fill lower energy levels before moving on to the next. But suddenly, you have lanthanum, who is skipping the 4f sublevel by going straight to the 5d sublevel. And second of all, cerium isn't even finished filling the 5d sublevel, and it suddenly wants to go to the 4f sublevel. So it goes to show how some electron configurations on this periodic table are quite unpredictable, and that is especially true when it comes to elements that have their last electrons in the d block and the f block. So we will look at exceptions to the rules we talked about, and of course lanthanum and cerium are one of those exceptions, but they're really hard to explain. So I want to later focus on some exceptions that are easier to explain, and since they're easier to explain, you should be expected to be able to understand how they work. But now let's go back to another topic. We are going to revisit quantum numbers. Before we revisit it, let's talk about this rule, the Pauli exclusion principle. It states that no two electrons of the same atom can have the same set of quantum numbers. So keep this in mind when you are comparing two electrons in an atom. So let's just say I want to find the quantum numbers for the last electron in sodium. So I'm going to draw some brackets and I'm going to figure it out. So we did do an orbital diagram for sodium. So let's look at this orbital diagram. The last electron is right there. We have to find the quantum number for that. So the first quantum number will be 3. And the second quantum number will be the one correlated to s, which will be 0. So we figured out the first two, so 3, 0. The third quantum number comes from doing a number line. So since the s sublevel has only one orbital, this will be labeled as 0. And since the electron is located on the orbital labeled 0, then we write 0. And the final quantum number comes from the arrow. It's pointing up, so it's positive 1/2. So you could write plus 1/2 or simply just 1/2. And I did this in the last video, so if you don't understand what I'm talking about, go watch the previous video. Now let's move on to another topic. We have to look at some exceptions to the Aufbau's principle. We already saw one with lanthanum and cerium, but of course those are completely random and they're really hard to understand, especially at this point in time where you just learned about them. So I will not go into those, but I want you to focus on 4 I want you to focus on chromium, copper, silver, and gold, because they have very special electron configurations that have a meaning to them, I guess you could say. So read this explanation. Sometimes filling half a D sublevel or an entire D sublevel is better than filling up a lower sublevel like S. And in other words, having half-filled or full orbitals is favored, especially for D sublevels. So let's take a look at chromium. Notice how chromium has an electron configuration of 4s1 3d5. Notice how the 3d sublevel is half filled because 5/10 is, half filled. And notice how the 4s sublevel is not completely filled. So it took an electron from the 4s sublevel because it's supposed to be 4s2 according to Aufbau's Principle, which states that you have to go from lowest to highest and fill everything. But in this case, we decided to move one electron from the 4s sublevel to the 3d sublevel, and we end up getting 4s1 3d5. Same thing for gold. Gold is 6s1 4f14 5d10. Notice how it's supposed to be 6s2, but it became 6s1 because it sacrificed one 6s electron to fully fill the d orbital. So if you write out the electron configuration normally for chromium, you get this. But if you want a half-filled D sublevel, then you move one electron from here to make that. And notice how if you write the electron configuration for gold normally, you get this. But since 9 is so close to 10, which is a full shell, it decides to sacrifice one 6s electron and turn it into that. So that's how you can identify these exceptions on the periodic table, and you should just look at these for chromium, copper, silver, and gold. Let's take a look at the next topic. Excited state, when one or more electron is above the energy level it's supposed to be at. So for example, the ground state of gold is written here, and remember, it's one of those exceptions to the ground rule states that we talked about, where the ground state for chromium and gold look like that because they want, half-filled or fully filled D sublevels. So, looking at this, if we promote one of its 4f electrons to a 4p sublevel, for example, then we get an excited state, which means that one or more of its electrons have promoted themselves to a higher energy level where it's not supposed to be at. So in this case, 4p1 is an electron that's not supposed to be there, instead it's supposed to be over here, and since it's in the wrong place, it's an excited state. So now that we talked about that, let's talk about something that might be confusing. So remember how if you write out the electron configuration for gold, naturally you get this. And when you move one 6s electron to the 5d sublevel, you get this down here. Let me just erase that and show you that. So wouldn't this circled in yellow, which is the actual configuration for gold, be known as an excited state since the 6s electron transferred itself into the 5d sublevel? Well, not exactly, because as a matter of fact, the electron configuration circled in yellow is actually lower in energy than this one, because even though the 6s electron transferred itself to a higher energy orbital such as the 5d orbital, this has lower energy. Why so? Well, remember, having half-filled or full orbitals is favored. Why is this favored? Because it's lower in energy. And if the 6s electron decides to transfer itself to the 5d9 sub-level, then it makes 5d10, and 5d10 is lower in energy, so it's more stable. And for this reason, this electron configuration here actually has a lower energy than the one over there. And remember, ground state just describes the electrons in their lowest energy state, and since this is in its lowest energy state, since filling up the D shell makes it stable, then this is the ground state. So now let's move on to a new topic. Atoms gain or lose electrons in order to obtain full outermost shells or sublevels. And they do this to become stable. So you might not get this at first, and I'll show you later how it works. But first, let's talk about something else. Let's take a look at this note. The distance from the nucleus is dominated by the principal energy level n. So remember how I told you that if the n is higher, then the electron is generally located further from the nucleus. And the bigger the n is, the farther away the electron is most likely to be. And this goes into a topic known as Coulombs Law. Coulombs Law tells you the relationship between electrostatic force, or the force between protons and electrons, the charge of the protons and electrons, or just any two bodies that have opposite charges or even the same charges, and distance. And force is in R, charge is in Q, and distance is R. K is just some constant that you don't have to worry about here. So, as you can see, this is Coulombs Law. It's an equation. And as you increase R, notice how the force decreases. And if you increase the charges of particles, then you will increase the force because they're both on the numerator. So that's just some interesting things that you can do with Coulombs Law. And now let's take a look at why atoms lose or gain electrons to be stable. So valence electrons are the electrons in the outermost sublevel or shell. They are typically the s and p electrons. So for example, in chlorine, this is the electron configuration for chlorine. And notice how 3 is the highest principal energy level, and thus that means that the electrons with the principal energy level of 3 are the valence electrons. So in this case, 3s and 3p are our valence electrons, and we have a total of 7 valence electrons. So how does this atom become stable? Well, in order to become stable, the atom has to gain or lose electrons to obtain a full outermost shell. So this shell is obviously not filled. It's 5 out of 6. So in order to get from 5 to 6, it can simply just add 1 electron. And then after, if you add 1 electron to chlorine, you get a chloride anion. And this chloride anion will have 1 more electron. But notice now that the 3s and 3p sublevels are completely filled. And in this note it says it filled the outermost s and p sublevels. So the outermost shell is filled, and this makes it stable. Just like how, remember as I said, the electrons in gold filled the d sublevel completely to be stable. And same thing goes for here. If chlorine wants to be stable, it can suck up an electron from the surroundings and, become an anion, but at the same time, it is able to fill its last sublevel and fill it up. And this is a proof for why chlorine is always -1. It's because it only needs to gain 1 electron in order to fill its outermost shell. So let's take a look at the next slide. Notice how the electron configuration for chlorine, when written in its abbreviated form, is just the electron configuration for argon. So notice how chlorine has the same electron configuration as argon, and as a result, chlorine is stable because, remember, argon is a noble gas, which means that it is super stable and doesn't want to react because, it has the right number of electrons, its outermost shell is completely filled, and I guess you could say argon is an happy element. So things that have the same electron configuration as a noble gas have the number of electrons to be stable and happy since their outermost shell is completely filled. So chlorine is happy because it has its outermost shell filled and it has the same electron configuration as argon. And since chloride and argon have the same number of electrons, you can call them isoelectronic, meaning that they have the same number of electrons. So that's a fun thing to keep in mind. And now let's take a look at the next topic, the octet rule. Atoms want a full S and P sublevel of the same N, or principal energy level, to be stable. So for example, sodium wants to have a full S and P sublevel, but it has that 3s1 electron. Does this mean that it needs to gain some more 3s electrons and 3p electrons to make it 3s2, 3p6? Well, no, because that would mean it has to get 7 more electrons, and that's pretty difficult for something like sodium. So what if sodium just lost an electron? And if it loses an electron, look at that. Its outermost shell, or sublevel, is now completely filled because 2s2, 2p6 is completely filled. So when sodium loses an electron, it becomes a sodium cation, and it's stable because its outermost shell is complete and it has the same electron configuration as neon. So yeah, some atoms like sodium like to lose electrons to be stable, and this is especially true for metals, since you memorize that sodium has a +1 charge, and now you know why. So the octet rule states that they want full S and P sublevel to be stable. And why is it called an octet rule? Well, an octet rule is named that way because the valence electrons, in this case 2s2, 2p6, add up to 8 electrons. So when an atom has 8 valence electrons, then it is stable. And in this case, sodium plus is stable because it has 8 valence electrons, as shown here. Now, there are only 2 exceptions. These 2 exceptions are H and He. These two only need a full 1s sublevel to be stable, since they don't have any 1p orbitals to fill up, since 1p orbitals don't exist. So helium is just, 1s2, and there's no such thing as 1p6. So it just needs to fill 1s2 to be happy, since these are its only electrons, so they're the outermost electrons, and they're completely filled, so it's happy. Now H needs to, be stable. It's 1s1. And how do we make it stable? Well, H could either become H+, where it has basically no electrons, and it could become H-, where it gains an electron to fill its 1s sublevel. So in this case, hydrogen can either gain or lose an electron to be stable, since having no electrons is technically still stable. So let's move on to the next topic. Let's write the electron configuration for manganese 2+, or manganese 2. So how do we do this? Well, we have to find the electron configuration for manganese. So for this question, it's nice to have a periodic table out, and it's nice to draw the electron staircase as shown here. And to draw it, well, just memorize it, and remember, just go down diagonally to find the order. So using these 2 pieces of technology, quote unquote, let's solve this question. In order to do this, we have to first write the electron configuration for manganese as it is. So for manganese, we have to take the previous latest noble gas, so manganese is right there, and the latest noble gas is actually argon, so I don't know why I wrote Me, it's supposed to be Mn, and this is Ar, and notice how argon has 18 electrons, so we need 25 though, so we need to add 7 more electrons. So how do you do that? Well, we have to go down the list. So argon is in the 3p area, so let's start at 3p, so 3p is right there, and the next stage is going to be 4s, so 4s2, notice how we're covering here, and then I'll go to 3d, so 3d, it looks like 3d5. So this is the electron configuration for manganese. It's also the ground state configuration for manganese. And how do you know whether this is one of those exceptions I talked about? Well, the 3d sublevel is half filled, and you don't need to move any electrons to make it half filled since it's already half filled. So we leave this electron configuration alone. So yeah, and it's also not one of the exceptions we memorized, and those ones that we memorized were chromium, copper, silver, and gold. And since it's not one of them, we don't do anything to it. So this is the electron configuration for manganese. Now, manganese 2+ is when manganese loses 2 electrons. So which electrons is it going to lose? Well, remember, it wants to lose the outermost electrons first. So I don't think I mentioned this, but you have to remove the highest N first, or the electrons that are furthest from the nucleus. So basically the outermost electrons. And in this case, the outermost electrons are going to be the 4s electrons. So we have to remove 2 of them. So in the end, manganese 2+ will have an electron configuration of argon in brackets and 3d5. And that's our answer. So let me expand this and write out the actual electron configuration separately. So this over here, the one that I circled, is the electron configuration for manganese 2. And notice how the 3s and 3p orbitals are completely filled. And this makes manganese 2+ very stable because, you know, the outermost valence electrons, and remember, valence electrons are the s and p sublevels, those are completely filled with 8 electrons, and that's technically stable because it follows the octet rule. And yeah, that's why manganese 2+ is stable. So let's look at one more example. Let's find the electron configuration for gold 3. Now, gold is one of the exceptions when it comes to electron configuration, so let's be careful about this. Gold, we have to write the normal configuration for gold, and according to the periodic table, gold is right here, and its previous noble gas is xenon, so let's write that. Xenon, and then after, what follows is, well, if this is 5p orbitals, then we have to start 5p, and then we have to go to, well, let's see, it goes to 6s. So let's start with 6s2. Actually, let's keep track of how many electrons we need left, since I like doing that. So we have 54 electrons for xenon, and gold has 79, so we have to add a total of 25 electrons. So let's keep a note of that. So after we add the 6s2, what's next is, well, I think it's the 4f that comes next. So 4f14, and then after 4f, it comes 5d, so 5d, now we have to be careful because we need 25 electrons. This is already 16, so we need 9 of these because 16 plus 9 is going to be 25. And is this the electron configuration for gold in its ground state? Well, no, because remember, it wants a full d orbital, and you know, there's only 9 of them, and it's so close to 10, so gold decides to steal 1 electron from the 6s sublevel, so it's going to be 6s1, and then 1 of the electrons from the 6s sublevel will go to the 5d sublevel, and this will be 10. So basically, 6s2, 5d9 becomes 6s1, 5d10. Now, 3+, it has to lose 3 electrons. So it will obviously lose its first electron from, oh wow, that's weird. I don't know why that happened. This is 6s1 and this is 4. So it's going to lose the electron that has the highest N first. So the 6s1 will go away first. So this will go away. And what's next after that? Well, xenon's electron configuration contains 5s2 and 5p6. So we have to find the next highest N. Well, we have a problem here because we have 5d, 5s, and 5p electrons to choose from to remove. So which one do we choose? Well, you choose the one with the highest energy level. So the highest energy level is going to be the 5d electrons because those are farthest along the staircase. And as you can see, 5s and 5p are behind it. well, let me just erase it. So 5s is here, 5p is here, and 5d is over here. So 5d has the highest energy out of the three. So we are going to take away electrons from the 5d subshell, and doing that, you are left with 8, and that's removing 3 electrons in total. So our new electron configuration will be xenon, and it will be 4f14 and 5d8, and that is the answer. So let's look at our final question, and let me just move this down because you got to see the question. It says, find the set of quantum numbers for the second to last electron of gold 3 in terms of energy level. So we have to write out the electron configuration for gold 3, and it's right there. And what's the second to last electron? Well, in terms of energy level, the order at which electrons go is from here to here. And the second to last electron is located somewhere in the 5d8, since that has 8 electrons, and the second to last should be somewhere in there. So let's draw out the 5d suborbitals in terms of their orbital diagrams. So we have 8 electrons, so we're going to do 1, 2, 3, 4, 5. And this is Hund's rule because remember, we are going to do single electrons before we pair them up in the same sublevel. So 1, 2, 3. And we have 8 electrons. And the second to last one, well, what's the second to last one that I drew? It was this one, wasn't it? So let's find the quantum numbers for that electron. So let's do some brackets. And what's our first number? Our first number is going to be this, 5. And the second number will be d, and d is equal to 2. And let's see, what's our next number? Our next number, we have to draw a number line. So 0's in the middle, -1, -2, 1, and 2. And since the second to last electron is over here, it's -1. And last but not least, is the spin positive or -1/2? So since it's pointing down, it's going to be -1/2. And this is the answer to the question. So I wanted to add one last thing. So remember the exceptions that I told you about, the 4 elements that I wanted you to, look at and remember as the exceptions, meaning chromium, copper, silver, and gold? Well, if you see any of these 4 elements and you need to find the electron configuration, remember that they are the exceptions. Now, for any other element that is not these 4 that I told you about, just do it as you would do it normally and do not move electrons around unnecessarily. Only move it when it is super close. Like, for example, this was I think 3d9, and this was 3d4. 4 is really close to half of 10, and 9 is really close to 10, so that's why I can move the s electron there. But for something like vanadium or nickel, please don't move the s electron to the d electrons to fill it, because that's not one of the exceptions. Remember, only do the moving of the s orbital electrons only for these 4 that I told you about, and maybe even for molybdenum, since I think that's an exception too, but I didn't tell you about it because I didn't want you to memorize too much. So that's all for this video, and have a nice day.